Hello, engineers. I hope you're having a good afternoon. In this opportunity, I'm going to explain the foundations for second topic of the course. This is about flow work and the energy of flowing fluid. Um, as I said in previous classes, all of the system that we're going to study is will be open systems, and in all of them we will have fluid. So let's begin. And remember, this is in the left side we have the basic representation of a control volume, and always a control volume involves the uh, the flow of a mass across the boundaries or of the borderline, the boundaries of the system. Yeah, it means that some quantity of mass must enter to the control volume, and obviously quantity of material will go out. So, um, in order to get the, the flow in or out of the system, there is need to apply or to apply some kind of work. Yeah, this is in order to push the mass into or out of the control volume. Yeah, so we can imagine the system such as an imaginary piston. Yeah, such as this is which is shown in the figure. Yeah, so we're going to consider a differential volume of the fluid, which must be pushed into the control volume. So we can apply a force such as we do in a imagine in a piston or in a range in order to get the mass into the control volume. Yeah. So obviously, if we apply a force and we have a displacement of this fluid along this distance L, the product of this force times the distance of the displacement is work. Yeah. This work required to get the fluid into the control volume is called flow work or just flow energy. Yeah, we use both terms indistinctively. So uh, obviously we can define too a workflow for the outlet stream. Yeah, again we need to apply a force. So in this case, it's such as a suction force in order to get some quantity of fluid out of the system. Yeah. So again, when we apply the force, we have a displacement of the fluid out of the control volume, and this displacement is related with the workflow for getting out the fluid into the uh, control volume. Sorry. So on the left side, we have a basic representation of the this imaginary piston in terms of the pressure. This pressure is the pressure which the flow exerts over the piston. Yeah. So in this case, if you have uh, tried to uh, apply some kind of force over of an range, you can feel that there is a force which opposites to the force that you apply in the range. Yeah, this force is related with the pressure. Yeah, because the fluid will apply a force in the countersense of the applied force. So in this case, this pressure, yeah, this force that we must apply in order to introduce the fluid into the control volume will depend on the pressure which the pressure of the fluid and obviously the cross-section area of the imaginary piston. Yeah. So in fact, in an open or an engineering device, we don't have really a piston, but this is a simplification or a single explanation of the phenomena. So if you remember, this pressure is just the force divided by the area of the piston. So we can define the force related with the flow work as the product of the pressure in the fluid and the area. So, as we said, the workflow will be the product of this force and the displacement that we get with the application of the force. So, in this case, we can calculate this workflow that we represent with a W letter and a F subscript, and the product of the pressure, the cross-section area, and the displacement. So this area or this product of the area times the displacement is just the specific volume or the volume of the fluid which we are introducing to the control volume. Yeah, so this is a very important definition because this is the way in which we can estimate the flow work for an open system. Yeah. So in the analysis of the control volumes, yeah, we used to use uh, a specific flow work. Yeah. This is the workflow done per unit mass of fluid. And this is just the product of the pressure of the system or the pressure of the fluid and the specific volume, the specific volume of the fluid. Yeah. So remember that the specific volume is a fluid property which is related with the conditions, specifically the temperature of the fluid. So if we know the pressure which a fluid is being introduced to the control volume and its temperature, we can uh, estimate the workflow. Yeah, obviously for the entering uh, or the outgoing uh, fluid. Yeah, a flow relation is the same regardless of whether the fluid enters or leaves the control volume. We use the same mathematical formula. So this equation allows us to estimate the workflow for the entering and leaving uh, streams in an open system. Yeah. So another concept important in the analysis or the thermodynamic analysis of fluids is the energy of a fluid. Yeah, it means the energy which accompanies uh, the flow of a fluid. Yeah, imagine that we have water going through um, pipe. Yeah, we know that this water uh, has uh, an energy by itself, yeah, which is related with the properties of the fluid, and an extra energy or some energy related with its velocity and with its position, yeah. So you remember from your basic thermodynamic course, um, we can define the total energy of a simple compressible system. Remember that a simple compressible system is that we just include three components or three components in its energy. Yeah, it means the internal energy, yeah, which is related with the motion of the molecules of the substance, and it's mainly related with the temperature of the fluid in this case. Yeah, the kinetic energy, which is related with the velocity of the fluid, and the potential energy, which is related with position within the fluid's per field. Yeah, it means the position of the fluid inside a reference system. Yeah. So if we include these three components in an equation, we can define, and this is, we usually use a specific energy. Yeah, it means energy per mass unit. And we can define this specific energy for each uh, simple compressible system as the summation of the internal energy, the kinetic energy, and the potential one. So, what happens, uh, or what happened when we have a fluid flowing through a control volume? Yeah. In this case, we need to include an additional energy contribution, that is the flow work. Yeah. Obviously, when we have this flowing fluid, we need this work in order to promote the motion of the fluid along the pipe, for example. So, in this case, this is an additional contribution, an additional energy that we are uh, uh, giving to the fluid. Yeah, so need to include this additional contribution in our previous equation. Yeah, so remember that this flow work, sorry, depends on the pressure and the specific volume. Yeah, so uh, remember that kinetic energy, in this case, as a specific unit, is just the half of the square velocity, and potential energy is just the product of the uh, acceleration of gravity of, and the position inside the reference system. And about the internal energy, uh, we don't have a formula or an equation for the calculation. It depends on the properties of the fluid. So we have some kind of correlation or some kind of empirical equations for estimated, but it depends on the fluid. So at this point, we need to remember an important concept that I hope and I suppose that you review in your previous uh, thermodynamic course. That is the conception or the concept of enthalpy. If you remember, enthalpy is related with the heat of um, substance um, at a constant pressure. Yeah. And we can define the specific enthalpy, sorry, the specific enthalpy, such as, yeah, this specific enthalpy is just equals to the specific internal energy plus the product of the pressure and the specific volume of the fluid. Yeah, this equation is valid for each pure substance in the nature. So, if you see in our last equation, here we have the internal energy and this product pressure times specific volume. So, we can uh, put together these two terms and rewrite the specific energy as the summation of the specific enthalpy of the fluid times its kinetic energy plus its potential energy. Yeah, this equation in red is that we will be using along the course for estimating the energy in the open systems. So please have it very, very uh, in your mind. So, this equation allows to estimate the energy, the quantity of energy which is transported by mass flow. Yeah, we refer the energy transport by mass as a phenomena which is occurring when a fluid flows through a control volume. Yeah, this flow uh, is transporting its energy through the system. So when we uh, get the fluid into the control volume, we are adding energy to the control volume. And when we remove the fluid from the control volume, we are removing to uh, its energy content. Yeah. So this quantity that we introduce or remove from the control volume, uh, because of the fluid flow, it's known as the rate of transport of energy by mass. Yeah, this is a rate of uh, energy which is being added or removed from the system. And we can estimate this from the specific energy that we have defined in the previous slide and with the product of the mass flow rate. Yeah. So we represent this rate of transport of energy, such as the letter E with super uh, superscript dot superscript. Yeah. So remember from the last equation in the previous slide, we have defined these three terms in the parentheses as the specific energy of the fluid flowing through the control volume. So when we do the product with the mass flow rate, we obtain this rate of transportation of energy by mass. Yeah. In the second equation, in the bottom corner of the slide, we I have just uh, uh, include all the term related with the kinetic and potential energy. Yeah, as occurring with the internal energy, enthalpy is a property of the fluid by itself. So we need to correlate this quantity with the properties or the thermodynamic variables of the fluid, such as pressure and temperature. Remember that this specific enthalpy must be looked for in a table or in a chart, or in some cases can be estimated from particular properties such as the heat capacities of the substance. Yeah, so we will recall some of these uh, equations for the estimation of the enthalpy. Finally, it's important to consider two important facts. When the kinetic and potential energy of the fluid are negligible, it means that enthalpy of the system, yeah, is the higher contribution. So it means that the specific enthalpy of the fluid is very, very higher compared with the kinetic and potential energy. Yeah, this difference must be in several orders. Yeah, it means, for example, this enthalpy could be 100 kilojoules per kilogram, and kinetic enthalpies, kinetic energy must be in the scale of units. Yeah, 1 kilojoule or 5 kilojoules per kilogram. Yeah, in this case, the higher contribution in the previous equation will be just the enthalpy, yeah, and the contribution of the kinetic and potential energy are negligible. Yeah, in this case, we can omit these terms in the equation and estimate the rate of transfer of energy just by the product of the mass flow rate and the specific enthalpy. So, finally, in general, the total energy transported by the mass into or out of the control volume is not very easy to estimate or to determine. Yeah, because this is because the properties of the mass can be changing with the flow. Yeah, along the time or along the process, the properties such as temperature, pressure, density, which are uh, related to the enthalpy width, uh, can be changed. In this case, we need to use integration to estimate this energy over a differential mass element and estimate the rate of energy transfer just by the integration of all the differential elements of the fluid. Yeah. So in the most of the cases of interest in engineering, these properties can be considered near to constant. Yeah. So we will discuss in the next topic in which cases this approximation is feasible. Yeah. So this is all for this video. If you have any doubt, please let me know. Have a good afternoon.